Welcome to this second session of today, and right now, we're going to talk about scientists in the cockpit. I'm with Philippe Baumier, Aeronautics Director at Onera. So first, Philippe, hello.
Good morning.
Good morning. And then the second question is, what is Onera and what is its mission?
Okay, so maybe, yes. Onera is the French aerospace lab. It stands for Office National d'Études et de Recherche Aérospatiale. It was created in 1946, just after the Second World War. And in fact, it has three main missions that are illustrated here on this slide. We have a first mission of innovation, to find innovation solutions for industry. And you have here an example on the left-hand side of a helicopter rotor blade. Maybe we can come back to this
Yes,
story later on. Our second mission is to think of the future, shaping the future, which means not only the next generation of aircraft, but the generation after. And we have a very intense activity in this field in order to reach the 2050 objective of climate neutrality these days.
Okay.
And the third mission is we act as expert for the government, because we work under the auspices of the Ministry of the French Armies, which means that, let's say, more than one half of our activity is in the field of defense, and the other parts are civil aeronautics and space. And we are a public establishment.
Exactly, so perfect transition. You're a public establishment, but what is exactly, where are you in the innovation cycle between academics, universities, and the CORAC?
Yeah, this is a very good point, because we are in a
special place, right?
Yeah, in a special place in this innovation cycle that is depicted here in this Paris Air Lab this year. In fact, when you look at the Onera logo, you see these two blue lines below Onera.
Yeah.
And this is an image of a bridge. So this is the bridge between the upstream research, so the academic research, and the downstream research and the technologies developed by industry. So our mission is to maturate these technologies with our knowledge base, with our scientists, and with our method and tools that we develop. So our activity is mainly between the technology readiness levels, TRLs 2 and 6. Last Tuesday, we had, for example, the chance to answer to a mission that was launched 1 year ago by the Ministry of Upper Education, asking us, Onera, to coordinate all academias and upstream research establishments in France in order to give recommendations for the future. So this is the most upstream part. And once these recommendations are given, we make the link with the industrial roadmaps, and especially the ones of CORAC, and Onera is also part of CORAC.
So you touched about the TLR, so the it's the
technology readiness level.
Readiness level, thank you. But that's a scale from 1 to 10, right?
Yeah, well, yes, 1 to 9.
1 to 9, sorry,
yeah.
And that's how an idea is ready to be a product.
Yes, well, beyond TRL 6, this is mainly industrial demonstrations or real flight demonstrations, scale 1 demonstrations, and okay, we are not in this field.
So that's the scale between like having an idea and having something that actually works.
Yeah, exactly.
So you talked about the three missions. You must have so many different projects to do and so many ideas to develop. How do you base the research you're doing? On what do you base that?
Okay, first answer is human resources, of course.
Yes.
We are more than 2,100 people, and about 2/3 of them are engineers and scientists. But our specificity, of course, is our experimental and numerical tools that we develop and we maintain. You have here the first kind of experimental tool that we have. These are, let's say, small rigs, maybe sometimes not so small, but that are operated by our scientific departments. What you see here is an icing wind tunnel that was built some years ago, and that is now operational in Toulouse, and that where we make studies to know how ice is accreted on aerodynamic surfaces in very well controlled configurations. So this helps the modeling of the models that industry is using then to size their systems and their aircraft. So this is just one example. We have many of them, of course.
Yes.
Very recently, we inaugurated a new facility in Le Foga to study the impact of fire in engines on composite structures, and I could quote more than 150 of them. So this is the first kind of experimental facilities.
Yeah, you have big ones as well, right?
Yes, exactly. We also have very big facilities.
The wind tunnel.
One of the most famous ones is the S1 wind tunnel, which is located in Modane, in the French Alps. So you have on the left a top view of this very big installation. You can guess how big it is to have this closed wind tunnel. It is, by the way, the largest transonic wind tunnel in the world, and it has some very interesting specificities. For example, well, it can operate up to Mach 1. So it's really interesting because you can test airplanes in transonic configurations, so in cruise configurations, simulating the real aircraft velocity. Maybe a few numbers because the test section is 8 meters.
Yeah, can you put a plane in the tunnel? Parts of a plane?
A scaled down, a reduced size plane,
Okay.
of course, yeah. But 8 meters diameter,
Yeah.
the test section is quite large. The power is 88 megawatts. So that's pretty large, and this wind tunnel is specific. So it's powered by counter-rotating propellers that are directly driven, so by a Pelton wheel with water coming from the lakes in altitude. So it doesn't need any electricity. It's just hydraulic power that makes the wind in the tunnel. So sometimes we call it the greenest wind tunnel in the world, and it's very much used by our industry. And another number maybe that is telling the mass flow can be up to 10 tons of air per second. 10
That's
tons of air per second in the wind tunnel.
Yeah.
So that's really large.
And we have a picture. So this is where you test, for example, the open fans.
Yes, it's very much used these days in collaboration with the Safran. We have a specific agreement here, and by the way, you can see here just behind an open fan,
Yeah.
and a version of an open fan. Well, several versions, by the way, of open fans were tested by Safran. Recently, during the last 2 years, and on the right-hand side, you see one of these open fans installed in Modane, in the test section, in this 8 meters test section, in order to measure the aerodynamic performance of the fan, so the thrust, the power, but also for acoustic properties. Because the wind tunnel has been modified to have better anechoic properties. It's not fully anechoic, but to have better acoustic properties. And you can make some nice measurements to evaluate the noise generated by this new kind of engines.
That's really amazing. And this is like models in like that you can touch, like proper models, but you're also working on digital tools, right?
Yes, this is the second kind of tools that we have, numerical tools. Maybe I can give some example of some of them in the following slides. So we developed our own tools in fluid mechanics. The examples that you see here is a tool that is developed in collaboration with Safran. It's the next generation tool, which is called Sonix. Why is it next generation? Because we anticipate the fact that the new computers will be quite different from the ones we are using today.
Yeah.
Today, most of the computers are based on CPUs. Tomorrow, it will be massively GPU based. And in order to take the benefit of all these new technologies, and maybe in the future, quantum
yeah, I was
technologies,
about to talk about that, yeah.
We need to rebuild the way we are developing the codes. And you have examples here of what we've been doing on the left on a centrifugal compressor of an engine, and on the right an exploratory computation for a reusable launcher. And what is interesting on the right is that we also take benefit of advanced methods, and especially on automatic grid generation. In former times, in aerodynamics, people were spending hours, weeks, sometimes months, generating grids around the surfaces in order to discretize the airfield. Now it can be done automatically, and our target is to go directly from the CAD to the result, which means that the engineer will really play its full role, which is not to generate a grid, but to analyze the solution and to improve the solution. And we are very close, and we already made some demonstrations about it to this target.
Yeah, because you're creating codes where you enter all the parameters that you want to test.
Yes.
So you're recreating like live experiments, but in a computer, basically.
Yeah. So another example is a collaboration with the Airbus and the DLR on an airplane. The code that is being developed is called CODA. And the specificity of this code and of this kind of application is that we need very accuracy, very small accuracy. When I talk about a small accuracy, is that we want to predict the drag of an aircraft within one count of drag. One count is 10 power minus 4. So this is very small. And to do this, you need very accurate method, and we are using higher order schemes for those who are a little bit familiar with this to get this kind of accuracy, even in cruise on the left-hand side, or in takeoff condition with all the high lift devices. We have other examples. I'm not. Oh no, it's not here. Okay.
So those are examples. So you use those codes for different applications. So we've seen fluid mechanics. What else do you develop them for? Everything.
We also develop our codes for structural mechanics. This is under development. It's also a new generation of code, and I think here the challenge for the future in structural mechanics will be to model all the scales of the materials, from the atomic scales up to the structure. This means different levels of scales, and make them communicate, and having the right modeling and between these different scales, because we need to go very much into the details if we want to understand, for example, how a crack appears in a structure and predict whether it's critical or not, and also trying to predict what will be the long life duration, what will be the life duration of a structure under very harsh conditions, the ones that are encountered in aircraft, in altitude, in an engine with high and cold temperatures and so on.
Yeah, so it's like zooming in and out in the material.
Yes, exactly, yes. Going very much in the intimity of the materials. Yeah.
So you have two examples of innovation, of cycles of innovation, as we say. I think the first one is the Blue Edge is the blue edge, right?
Yeah,
Blade.
I think I would be able to speak during hours about this this example because well, this was most of the part of my scientific career. But I think it gives a pretty good idea of what is innovation cycle,
Yeah.
and what is our role as a research establishment.
So the whole innovation cycle from the idea to having something working, how long did it take?
It took more than 25 years, between 25 and 30 years. So it started in 1991, in fact, when Airbus helicopter, at that time it was Eurocopter, by the way, came to us on ERA as a research establishment and told us, okay, we would like our waters and our helicopters to be less noisy. Because, you know, helicopter is noisy, especially in descent flight conditions. And the question was, okay, research establishments, on ERA on the French side, DLR on the German side, because Eurocopter has activities in both sides of the River Rhine. Please propose us something. Do something. What ideas do you have? And so we started almost from a blank page, because at that time in 1991, where we had an idea of the noise mechanisms, of what was annoying in terms of noise, but we didn't really know how to predict it. Yeah. We knew it had something to do with blade vortex interactions. You know, when you hear a helicopter that is landing, you hear some kind of flap, 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 something like that, which are blade vortex interactions. But we didn't have the tools to model it, or let's say the tools were really basic. And since the question was, how can you reduce the noise, the first step was to understand.
Yeah, so you had to create the tools and the innovation.
Yes, exactly.
Yeah.
So we had to both develop the tools, understand the physics, develop the models, and try to find good ideas on how to reduce these blade vortex interactions.
So can you quickly walk us through the different steps of the cycle? So
I think around 1996, we came on the upper left of this slide.
So the try in the wind.
Sorry?
So it's the tries in the wind turbine, right?
Yeah, on the upper. No, not on the wind tunnel. On the upper left. Yeah. To this concept of blade, which is no longer rectangular, but which has this shape with a double sweep. One part is forward and one part is backward. And on the paper, on the screen, as a result of the computations, this blade was supposed to have more than 50% of noise reduction, which is quite large, more than 6 dB, between 6 and 9 dB, which was the target, by the way, 6 dB that was given by Airbus helicopter.
It sounds small, but it's actually a big change, right?
But it makes a big change because 6 dB represents
decibel, right? dB is decibel.
Sorry, dB is decibels. Yes. So it's cutting the intensity of the noise by a factor of 2, which is very large in decent conditions. But it's good to have it on the paper. It's another story to prove that it works. So an intermediate step was to go to the wind tunnels. And again, we went to the S1 wind tunnel that I already presented for high-speed tests. And also in the DNW LLF wind tunnel to make some acoustic tests. And the results of these tests were obtained in 1998. And they were really amazing. It really confirmed the very nice and the very high noise reductions that we had on the paper, which means between 6 and 9, depending on the flight condition, depending on the descent angle of the helicopter.
So 7 years for the first step.
Yes, this was the 7 years already. And at that time, even if we were discussing with Airbus helicopters, when Airbus helicopters, Eurocopters saw the results, they say, oh, this is really interesting.
Okay.
And they really started to be such interested that they say, okay, we need to go further now, beyond the exploration and the maturation. And so we went together to see our official services, so the French DGA and the DGAC, in order to have more funding, to make the proof that we can upscale this concept, because this was a model water. The water that we tested in the wind tunnel had a 4.2 meters diameter. A full-scale helicopter has an 11 diameter length. And so it was also a long story because we needed to adapt to some industrial constraints. So we worked with industry. And to make it shorter, not to be too long, in 2007, Airbus helicopters made the demonstration in flight on a EC-155 that it worked in flight. We had noise reductions, a little bit less than expected, between 5 and 6 dB.
Okay.
But we had a strong improvement in terms of performance. We had 4 dB, 4 decibels in noise in distant flight, in 6 degrees distant flight, and an additional payload of 150 kilograms, which is quite large. You know, 150 kilograms means 2 packs, 2 more people in the aircraft. So it was really great.
So that was 9 years, and then?
And then between 2007, yeah, there were an additional 8 years, because it's good to make a demonstration, but then, of course, an industry has to have a program. And so they started the H-160 programs later on and decided that this helicopter should have this kind of blades. And the first flight happened in 2015, and the helicopter, the civil helicopter, the H-160, obtained its certification by EASA in 2020. And in the future, there will be a military version called the Guépard that will equip our armed forces, replacing all the light and medium-sized helicopter of the French armies.
So how long would it take now? Because you have more tools, you also have AIs, you have coding that is like, that probably take like half.
This is a question I always have. What would
happen?
It
would take a shorter time, right?
Yes, definitely it would be short. It would be, if we had to redo it, it would be shorter, because now we know the physics, we have the tools. We would use maybe a more intense use of high-order methods using computational fluid dynamics that we didn't really have at that time, and at least the first phases would be much shorter. But I'm not sure that artificial intelligence would really help, because I would bet that an artificial intelligence would not have the idea to have this double suite concept, because it will not invent it. It didn't exist before. So I don't know how an artificial intelligence would say, okay, let's try this one. It cannot invent it.
It could support some of the steps maybe,
exactly,
but not create it, obviously. You still need a human brain, you still need scientists in the cockpit.
Yeah, you still need your brain.
Exactly.
Yeah.
We are going short on time, so I think we're going to switch to the next example.
Yeah.
So not all the innovations go to the full cycle. Sometimes you have to stop. But you learn from them, right? Can you move to the next one?
Yeah, it's the story of the open waters, which is ongoing, but which started maybe 10 years ago. We started by studying, especially in the European context, together with Safran, by the way, what we called at that time counter-rotating open waters. So it's an open water, so it's not a ducted fan, but with the 2 rotating, counter-rotating blades.
It's over there, right? No, it's not this one?
Not this one. This one is not counter-rotating. This one behind just has 1 rotating and the fixed vane behind. But we started with this counter-rotating open water. We developed our knowledge base. We made a lot of aerodynamic and acoustic simulations. We understood what were the noise mechanisms. And by the way, Safran also made a ground demonstration. This is on the top right picture here in the Clean Sky 2 partnership. And this was really a great experience. But the decision at the end of Clean Sky 2 was stop, because there were some issues with respect to the weight of such a system, and the integration on the aircraft was not so easy. So we had to stop the studies. But yeah, what are we doing now? Today, what is on the table for the next, as you know, for the next medium-range aircraft is what we call the unducted single fan, which is not a counter-rotating open water, but it's open. We have a big fan ahead, and we have a fixed, instead of a rotor behind, well, we have a fixed propeller, fixed vane. So all that we learned on the counter-rotating open water is definitely not lost. We use our knowledge to develop much faster the open water together with Safran. So the message here is research is not something straightforward. You need to investigate many things, and sometimes you come to a dead end. But what you've done is not lost. You have to think of, okay, did I miss anything, and how can I use my knowledge to make something better? Yeah. And this is what is happening these days between the counter-rotating open water and the open fans.
Best case scenario, you produce a product or something that actually works and gets integrated. Worst case scenario, which is still okay, you produce knowledge that you will use later. So it's never really lost, right?
Yes, exactly.
Thank you. I think before we take a few questions, where can we see the innovation? So the RISE is just over there.
Yeah, but...
Do you have other things you want to point at?
I think I'm just quoting my CEO, and I think he would be very happy about this, although he's not here. Bruno Saint-Jean, who is the CEO of Onera, he said that all the major civil and military aerospace programs in France and Europe carry a part of Onera's DNA. In Ariane launcher, on all Airbus aircraft, on the Falcon, on the military aircraft, like the Rafale, on missiles, on helicopters, engines, radars. You have some Onera inside, and some research, deep research inside. And the public doesn't really see it, but I think it's really worth reminding that without research, the technology cannot develop, without upstream research. And these days, we often hear the message, you need to make it fast, you need to have something that has impact. Yes, okay, this is true. But you also need to remember that sometimes research can take sometimes longer than expected, and that it is really mandatory.
Thank you. I think it's a great message to finish this conference. So thank you, Philippe. We're going to take, do you have questions?
Est-ce que vous faites des ponts avec d'autres secteurs d'activité sur la recherche voilà.
Oui, alors effectivement, je réponds en français ou en anglais du coup? En français. Non, mais c'est bon. Oui, alors effectivement, il y a des technologies qui ont été développées chez nous dans certains départements qui ont essaimé dans d'autres domaines. Alors dans le domaine médical, par exemple, on a un certain nombre de retombées. Je pourrais aussi citer un exemple d'une start-up qu'on a créée dans le domaine des éoliennes grâce à des lidars. Ils ont développé un instrument pour aider, pour quantifier en fait l'intensité du vent, pour mieux localiser l'endroit où doivent être situées les éoliennes. Donc ce sont des instruments qui initialement ont été développés pour l'aéronautique et qui finalement sont utilisés pour dans d'autres secteurs. On a pas mal d'exemples. Alors tout n'est pas des success stories, mais effectivement on essaime dans d'autres secteurs que le secteur aéronautique.
Merci. On a le temps pour. We have the time. Sorry, switch to French. We have time for one more question. if we have any? No, I think you're good. Very good. Thank you very much, Philippe.
Thank you.
Thank you, everyone.